the real numbers. The real numbers are all of the numbers from minus infinity to 0, all the way to positive infinity. The real numbers include all the counting numbers, in other words, the positive integers, 1, 2, 3, 4, 5. The negative numbers, okay, minus 1, minus 2. The negative numbers being, for instance, what number plus 2 is equal to 0? Well, it would be minus 2. Okay, so that gives us the negative numbers. Ratios of these integers, which we call rational numbers for some strange reason, and even numbers which are not expressible as ratios, which conversely are called irrational numbers. So what am I going to talk about next? It's the fact that there are many ways to represent numbers. We're not going to use all the methods I mentioned below, but we're going to cover them each just so that when we reach decimals, fractions, and percentages, these are all different ways of representing numbers. You'll have some background to understand when I say that a single number can be represented in several different ways. Let's say we're talking about half of some quantity. Maybe it's half a tank of gas. Maybe it's half the time it takes to complete some other task. Maybe it's half an area, like say you have an acre and you're talking about half an acre. Okay, in percentage, fractional, and decimal notation, these are 50%, 1/2, and 0.5. They all represent the same number, 1/2. And they all have different uses, and some are better for some applications and some are better for others. Okay, so let's talk about the earliest representation of numbers. These are tally marks. They're just little scratches either in a stick or on the wall of a cave or something like that. And it actually works pretty well. If you're a Viking shipbuilder, you have a stick. It's called a memory stick. You know that the length of the ship has to be at least 9 times the width of the ship. So you take your stick and you measure out the keel. It's got to be at least 9 times the width of how long are you going to make it. And so on and so forth. And you just move forward. You can modify this a little bit. When you have your scratches reach a group of 4 scratches and you count one more, you put a slash through it. And it makes it easier to count the tally marks. 5, 10, 15, 20, because you have groups of 5. Okay, you've seen something very much like this in a cartoon about a prisoner in a cell keeping track of the days. In this case, addition and subtraction are easy enough. You simply add or erase the appropriate number of marks. Roman numerals are very similar to tally marks, okay, but they use the letters V and X for the numbers 5. Of course, there are other shorthand notations as well. There's a symbol for 50 and 100 and 500 and 1,000. It's a kind of shorthand. Imagine expressing the year 2018 in tally marks. Well, that would be, you already see that we need something better than tally marks. In Roman numerals, it would be MM, X, V, I. To be clear, the M stands for 1,000 and MM stands for 2,000. The X is 10, so already we're up to 2010. A V gets us to 2015, and then 3 more gets us to 2018. A couple examples. 3 vertical slashes, or 3 vertical marks, that's 3, or the capital letter I. A V for 5 and 2. 5 plus 2 is 7. 5 plus 3 is 8. We have X representing 10, and XV representing 10 and 5, or 15. You can see how addition is fairly easy with this too, because its addition is implied in the structure here. So 10 plus 5 plus 2 is 17, and then of course add another X and we get 27. While Roman numerals are more compact, some operations are made harder. Addition and subtraction are still feasible. Okay, so like I said, addition and subtraction are still kind of built into the system. All right. With multiplication, it's a complex undertaking, and long division, let's just say that you could be a very learned person and not know how to do long division. Very learned person in the medieval world and not know how to do long division. Our modern system uses numerals like 0 to 9 and a place value to represent numbers. The number 300, whoa, I need to correct that. 523 is understood to be 5 100s, 2 10s, and 3 ones. We might even write that out as 523 is equal to 5 times 10 to the 2, or 100, plus 2 times 10 to the 1, which is just 10, so 2 times 10, which is 20, 3 times 10 to the 0, anything to the 0 power is just 1, so 3 times 1, and we add those all together, it's 523. We call these the Hindu Arabic numerals. They've been around since about 500 AD. The form that we think of as is what we would recognize to be 0 through 9, originated in North Africa. If you go to the Middle East right now and you look at Arabic numerals, they're not going to look the same as what we use. Okay, but they came from North Africa, made their way to Italy in the Renaissance about 1200 AD. And if you look back about 1200 AD, you'll notice that something very interesting happens in Italy about 1200 AD. Italy becomes very, very prosperous. Okay, the procedure for addition and subtraction are quite clear, and recognizably similar algorithms are used to multiply and divide numbers in this representation. So you might ask yourself, hey, is there some maybe a connection here? And you might say, oh, hey, double entry bookkeeping, which involves a lot of addition and subtraction. Okay, you're moving a quantity from one column to another. That requires a lot of addition and subtraction. It's called double entry bookkeeping, and it was made possible by these Hindu Arabic numerals. And so essentially the economic explosion that occurred in these tiny little Italian city-states that eventually became what we call the Western civilization. All right. Okay, we've already mentioned the whole numbers, also the positive which are called the positive integers, which are 0 to positive infinity. If we ask the number 2 plus what number is equal to 0, we answer that question by inventing the negative numbers. Okay, so the answer of course of that is -2 or -2. We would write that with a dash in the front, so -2. The integers from negative infinity to positive infinity, these are the whole numbers. Rational numbers. These are numbers which can be expressed as a ratio of two integers. The rational numbers include numbers like 1/2 and 3/4. Of course, a number like 100 over 50 is also a ratio of integers. And if we carry out the division implied by this slash mark, that ratio is equal to 2. Thus, every whole number is also a rational number. The irrational numbers. There were a group of Greek thinkers called the Pythagoreans, and they had this very curious idea that the whole world could be represented by integers. And then at some point, someone asked the question, what number times itself is equal to 2? Well, you can look up proofs that the square root of 2 is irrational, or you can just simply, we can just move on from there. But they found out that the answer, what number times itself is equal to 2, could not be expressed as a ratio of integers. They were a bit annoyed by this. And as a matter of fact, the gentleman who, well, there are stories of thinkers being thrown from cliffs. Okay, and you can look that up on YouTube if you like. Okay, the irrational numbers cannot be expressed in a finite decimal form. So the following are only approximations. So the square root of 2 is 1.4142, and then there's a whole bunch of numbers after that. It just keeps on going forever. Pi, 3.1415, and it keeps on going forever. E, that's the natural number. It's involved in logarithms and exponents. And 2.78182, and it just keeps on going. And the golden ratio, sometimes you'll see it mentioned in artwork or spirals or natural systems, like how the distribution of the spiral pattern of seeds in a sunflower, 1.618. They're all useful for describing those. So I'm going to let you go now. We've described the scope of the real numbers. We're going to move on to addition and subtraction, and our third video will be about multiplication and division. But I think that's enough for right now.